Hi guys, and welcome back to my channel XYZ Architect. I'm Marius, and today we are going to talk about the qualification of the measuring spheres from the CMM. Just to make sure that we are on the same page from the beginning, in this channel we are going to talk about the coordinate measuring machine most of the time, because this is what I'm doing right now. I'm working on a coordinate measuring machine, and what I am doing for the last 5 years now. So we are going to talk about, of course, other measuring equipment, but most of the time we are going to talk about measuring on the CMM. So as I said earlier, today we are going to talk about the qualification of the measuring spheres from the CMM. So let's see what the qualification is all about. So, why do we need to qualify our probes? Well, each time the probe comes in contact with the surface, the extension of the probe has a deformation. So the software needs to know that deformation in order for it to correct it. So for each type of probe and for each position in the measuring space of the machine, we need to do a qualification. In order to do a qualification, we will need a reference sphere. The reference sphere is a highly precise object with precise form that comes with a calibration certificate. The reference sphere is put on the measuring table in a manner that is easily to qualify all angles of the probe. The qualification operation identifies the radius and the center of the stylus sphere, taking in consideration the reference system of the CMM, or the 0 point as it is also known. So after the measurement of the reference sphere, the CMM knows the center of the stylus sphere and the dynamic radius of the stylus sphere. And just as a recommendation, in order to be sure of the qualification, you can measure the reference sphere. You can measure the diameter of the reference sphere and the form of the reference sphere and compare the results to the calibration certificate. Okay, so now that we know how to do a qualification of the measuring spheres from the CMM, let's talk about the interval time that we need to do this kind of qualification. There is no rule to say how often we have to do the qualification, but we do have some recommendations. So let's say that your CMM is used on 3 shifts, then it is recommended to do a qualification on each shift. Or let's say the temperature in the room is 1 degree higher in 1 hour, then you have to do a qualification. Or 2 degrees higher in 24 hours, then again you have to do a qualification. Another good example is that if the CMM has a big collision, and I mean a collision that makes the CMM stops, then you have to do a qualification as well. And the last recommendation is that some time has passed, for example 1 week. We have to talk about the importance of the temperature in the measuring room. So if the temperature changes in the measuring room, this results in changes of the position of the measuring sphere of the stylus. So the more complex the architecture of the stylus, the more is exposed to the influence of the temperature. I have put together an example of what means to have just 1 degree Celsius difference in the measuring room. Okay guys, so as I promised, I have made an example of what it means to have 1 degree Celsius difference in the measuring room. Okay, so this is the formula of linear deformation. In order to better understand it, I have explained every element that compounds the formula right here. So we have the delta L, the linear deformation. We have the alpha, the coefficient of thermal expansion, L0 initial length, and delta T temperature variation. Okay, so the example is formed from an architecture of 2 styluses. They are formed from a Titan block in the middle, aluminum extensions right here, and stylus extensions right. The linear deformation for one element for 1 degree Celsius is calculated like this. The steel with a length of 80 millimeters, we have the coefficient. By the way, you can find the coefficient for every material online, so go Google it. It should be right there. So this is the coefficient for the steel, and the result of linear deformation is 0.44 microns per degree. Then for the aluminium with a length of 100 millimeter, this is the coefficient of thermal expansion, and we have the result of linear deformation of 2.3 microns per degree. It's the biggest element from the architecture, so it has the biggest linear deformation. And also the Titan with a length of 20 millimeters. This is the coefficient of thermal expansion for the Titan, and we have the linear deformation of 0.12 microns per degree. So the linear deformation between stylus 1 and stylus 2 is 5.7 microns per degree, because we only calculated, remember, we only calculated the linear deformation for one element. So if we multiply these results by 2, we get 5.7, roughly 5.7 microns per degree. But if the temperature is deviated by 5 degrees in the measuring room, we will have an error of 28.5 microns. And we are just showing the errors from the stylus, guys. If you combine the results with the thermal expansion from the measured part, you can have significant measurement errors. So do be careful with the temperature. I hope the information provided was helpful. If you like what I'm doing, please leave a like, share and subscribe. Until next time, have a nice one.